All right. Welcome, everyone, to Wolfram Institute live stream. It's a great pleasure for me to have, well, mostly all the team here today to hear Richard's summary of research. This is research that happened under the sponsorship of MetaMetaverse, and Richard's fellowship was funded by this party. And moving forward, Richard's funding is going to come from a different source, so we're going to change a little bit in that direction. But we wanted to take the opportunity to both see all the work that Richard has done in the past and have a chance for newer incorporations to the Institute to also maybe comment on it. Obviously, I was there to most of Richard's work when it happened, but James wasn't and Xerxes wasn't, and they are here today, also Nick, to ask questions and comment on it. So, but beforehand, maybe Richard can give us an overview and sort of display all the work, and I'll just forward that the materials of this and the outputs of this research will be available at some link. You can check back on this YouTube video for a link in the coming weeks or days, maybe even. And for sure, as I always say, do join our community. We have a very lively and interactive community on our Discord channel and Discord server and channels, and you can join by just hopping on the website community tab. So that's another way that you could access all these materials if you're interested, or indeed contact Richard and discuss them. So without further ado, Richard, take it away.
All right, thank you, Carlos. Okay, so this notebook actually was sent to me by James on my first day, and it was a sort of brief of the kind of research question.
Richard, wanted. Are you sharing the screen? I don't think we're getting.
Sorry, yeah. Because I rejoined Discord, it stopped. No worries. Let's get it back up. Thank you for that. Thanks.
No worries.
Now we can see the notebook that James. So this was sort of prompting my research at the Institute in the first half, in the sort of first 6 months, where essentially James wanted me to look at this idea of sort of abstracting away from the underlying computational system and looking at some kind of continuous aspect of, say, causal graphs. Like, how could we approach that question? And so he was bringing up this idea of moduli spaces and so on. So this notebook will be sort of part of that bundle. And I think I've summarized it fairly well. We don't need to kind of go through it. Now I have 20 notebooks open to kind of go through, which is a subsample of all of the working notebooks, many of which are kind of quite messy because you're just, trying to figure out some result or something. So you have some sort of partial result or some code that's work in progress. So we, but we want to give a kind of sort of rough idea of kind of what it's like to be at the Institute, what it's like to do research and things like that.
That's right.
So let me figure out which one to jump to next. We can jump to the summary that I made after that period in the handover to Stephen, and then subsequently sort of drill into some of the working notebooks. So when James left the Institute, I was sort of tasked with giving a brief summary to Stephen, so I think that might be quite useful here.
Yep.
And one notion that we had brought up was this idea of a kind of minimum cost edit distance between graphs, which for any kind of causal graph allows you to, or any pair of causal graphs allows you to get this integer, basically, that sort of describes their edit distance. And given a matrix of that, you can do this kind of high-dimensional embedding. So in some sense, this matrix, the resulting embedding allows you to kind of continuously sort of move around this space, or at least organize them with some kind of neighborhood structure, so that sort of similar causal graphs live in the vicinity of similar causal graphs. And let's see where we got to with that. Another issue another topic that we sort of looked at for this was this idea of graphons, which are sort of limiting process of some graph construction process. So take an adjacency matrix of some graph, take the graph to its limit, and now you have some function on the sort of unit interval, which gives you the sort of density of edges between any two vertices. That isn't without problems, though, because you need to find some sort of natural ordering of vertices, and there are some issues with measure rescaling, which I think have kind of more formally been tackled within the sort of infrageometry project that is, which has kind of come around since, more recently, where you have to decide on sort of on what basis are you performing some kind of rescaling to kind of keep everything within it.
Richard,
to avoid infinities and so on.
One brief question. Are you showing are you talking on a notebook that is not the summary that James Boyd gave you back in the day?
Yeah, I actually have switched, but
okay, but
so if you're not seeing it, then
on our end, yes.
Okay. So Discord is showing me that. So let's try starting the stream again and see.
Yeah.
Capture voice. Scroll out.
Now
it's changing.
That's
if you see it pausing, I'll be sort of scrolling, and if you see my mouse not moving, then we'll just have to do that again.
There we can see a desktop, so it's likely that this is going to work now. Because before, I think we were seeing the individual notebook.
Right. Okay.
Good.
Cool. Thanks. Okay. Yeah. Apologies. I've been talking whilst looking at this, which gives you a sense of what I was talking about. So I'll retrace my steps. So this is the edit distance matrix for a set of causal graphs. This is some embedding of a random sample of causal graphs from some multi-way system. And here was a kind of visual description of what a graphon is, which was my notion of being able to define like a kind of continuous treatment of this question from James. And we had this, I remember it was an idea from Nick where we would sort of take some known manifold and sprinkle it and sort of look at what it looks like if you start taking higher and higher number of vertices or higher degree of sprinkling and so on to see what can you kind of fit a function to that and somehow parameterize this function based on the original say the coefficients of this manifold. And if there's some sort of relationship between the two. There was some discussion around, say, self-similarity, because in particular systems you get, this kind of, trivially you often get this self-similarity. In this case, this was just a Kronecker graph, but there weren't. So, for example, if I was playing around with, say, context-free grammars, quite often they ended up with very self-similar looking adjacency matrices. Then I had this kind of foray into, so actually, let me see if I have it loaded up. Yeah, so I had kind of noticed that, say, something like collats, where you have this collats graph, and you can grow that as large as you like, or have the computational budget to do so. Does it make sense to ask what would the graphon for the collats graph look like? Which, after a while, I bumped into Conway's stuff on Fractran, and then I recall that, okay, the programs in that world are just a list of rationals, and, okay, it's not quite continuous, but it's a much easier thing to grasp in terms of a space. Well, actually, and I'll put in quotes, space. It's not a space in the strict mathematical sense, but it's in the sense that one has a kind of natural ordering, but it's a little easier to work with than, say, hypergraph rewrite rules where there's no kind of natural order. And actually, like looking at these systems in a multi-way sense gave some interesting results. So, for example, these were programs performing different computations. I forget which. One of them was addition, one of them was multiplication. And when you start out from different sort of initial states, you get these interesting diagrams where the programs kind of move in sort of similar trajectories and then sort of bifurcate when they're doing something unique to their particular input.
Is that a continuous collapse?
No, but you could again, you could think of this graph as being some sort of subgraph of an infinite graph, which represents sort of all the space of all possible inputs to that particular program. So yeah, there exists some graphon which describes this program. It's hard to yield that thing as a kind of concrete object, but looking at a small slice of it, we actually have a kind of multi-way system. So it's a slight variation on Fractran, because Fractran gives you a strict evaluation order, similar to, say, something like the lambda calculus, where it's like leftmost, outermost, or similar. What I was doing here was just for any element of the Fractran program, if the current state could multiplied with any of those elements gave you an integer back, then I treated that as a kind of valid transition, which is kind of breaking. Normally with Fractran, you start from the first element and you work your way along until you get an integer given your current state and that element. So yeah, this was a kind of like multi-way Fractran. Sort of applying all, and so you can think of each of the fractions as a rule or some subcomponent of the rules, and then you get this multi-way sort of state space. The nice thing is that the states are kind of interpretable because they're just registers which are stored as exponents of these primes.
There's a concept that even odd for non-integer reals would need defining.
Say again, sorry, I couldn't quite hear it.
Even odd for non-integer reals would need defining.
Even odd for non-integer reals.
Yeah.
I'm not really sure what you're trying to say.
Okay. Just a comment on the YouTube chat there by Dugan.
Oh, okay. All right. Sorry, you're relaying chat. Right. Yeah, I did think about this. Like, could you extend Fractran to sort of like the next level up and so on? But it's kind of intractable, computationally. Yeah, I mean, we don't even use real numbers in a way. We use this approximation to them by IEEE floating point numbers. But yeah, I did actually play around with this. Like, what happens with because Fractran is like the integers over Q or something, and what would happen if you were working in the reals and you were testing for integer or even complex domain, I was thinking, but I think that's going to firmly live in like theory land and not be something that you can work with unless you have, I don't know, analog computation to hand or something like that. And then another thing was kind of spectral, like some sort of graph spectral method. So this was like the graph Fourier transform actually, and was looking at, for particular systems, can we sort of identify distinct features? And I mean, this stuff is a while ago, so I can't even really remember what the findings were, but I do remember that, some of them had kind of, there were sort of outliers here, and there were some systems which looked to be kind of clustered together.
Just to clarify, Richard, I think it's good to do a scheme. It's not necessary to just extensively. It's probably going to summarize.
Sure.
Because I think it's better to see a lot of things than to necessarily go into.
Exactly, and that's why I've jumped to this research summary for Stephen rather than getting into the working notebooks, because I pulled everything out. So this is actually a quick way of dealing with that first six months. I remember that there was some talk about compiling between different systems and trying to find some sort of like morphism between them and so on. So I briefly looked at like self-interpretation, because I found that quite interesting, and there does exist a self-interpreter for Fractran programs where you can sort of encode your program and then feed it to this program, and the self-interpreter will evaluate your encoded program. You sort of encode it by this scheme here, then you run this thing, and then there's a certain sort of way in which you read the states out. So you can sort of think of this program as being kind of embedded, and if you have enough memory, you could probably embed it like several times. So the particular computation was maybe just adding two integers or something, which would take some small number of steps. But then, when you're in a self-interpreted regime, now you take much larger steps. Your graph grows much larger, and as you nest, you're kind of heading towards infinity, or where you want to end up. Yeah, and actually this was a sort of internal state diagram. I forget which particular program it was, but this is kind of looking at the program sort of as it's executing and working out its result as it's going. Right. It didn't need to be a 3D plot, but anyway.
It's nice.
There you go. Yeah, and then there was... I do recall that we were looking at some notion of entropy as well. And this wasn't a kind of sort of formal treatment of it, because I remember there was some... Well, especially with regard to hypergraphs, it's quite a difficult question, and there's a lot of higher order considerations that need to be treated carefully. But as a kind of rough thing, was looking at the behavior of these programs and their entropy with respect to like the graph size and the inputs and so on.
Richard, do you remember whether there was some kind of notion of second law, when you can show at least numerically where the entropy increases?
Right.
You do something with it.
I don't really remember. I just remember that the scaling was very different, and that's kind of demonstrated by these two programs having slightly different sort of curves. But I don't remember, to your question, ever sort of seeing anything exactly like that. And these were things that sort of like... Sorry, go ahead.
Yeah, I'm just asking because I kind of stumbled on one recently.
Right. Let's hear about it.
It's just about if you do the discrete... If you deal with just categorical distributions and when you apply some stochastic matrix, you kind of show that it always decreases your entropy, increases the entropy.
Right.
Couldn't find like a good proof of it.
Mm-hmm.
But it just
interesting.
Holds.
Yeah. Actually, that kind of relates to something I was hearing sort of Stephen talk about in the sort of larger second law discussion about, you could go from a higher entropy state to a lower entropy state, but it seems kind of unlikely that you would find the exact, that set of states that might take you to lower entropy is probably quite small versus the full set.
In that simple numerical experiments I've done, there's like if you have a stochastic matrix that with rows and columns both sum up to 1, you always have a second law. Like for every probability distribution, your entropy increases. But when you just have a row stochastic column, when you kind of only rows sum up to 1, then there may be some states that actually decrease in entropy.
That is interesting. Cool. Yeah, thanks. That's something to think about. Is there a name for a matrix which has a row and some property? I don't know.
Usually it's either doubly stochastic or bistochastic.
I see. Yeah. Now, I do remember this... so, I mean, for a while I'd been thinking about kind of... I mean, the whole question is about sort of spatialization and so on. Like, James is talking about moduli space, and I even think I put this question... I mean, Xerxes is here, but I believe during the winter school I put this question about, is there some way of sort of endowing Rulio space with some topology by going to rules which modify rules and sort of infinite tower of such a system or something, possibly connections to infinity categories. That was one notion. Let's see here. And this particular reference I remember being quite interesting because it makes this statement that sort of programs in the discrete world are actually sort of their statement here is that they're singularities of analytic varieties, which builds bridges to other sort of disciplines within mathematics, which could be quite interesting to explore. And I haven't done a kind of deep dive, but this particular paper has a kind of I think they're working with some sort of continuous relaxation of a Turing machine. Let me just make this larger. And for some reason I thought it was relevant. I think it is or could be. But you can check that out, and we'll provide links to that, or you can go off the title. So
let me just add here, Richard, just a comment. I think it's not even a comment of what you were saying, but just to contextualize a little bit to the viewers and to the new incorporations of the Institute. This stream of ideas of Rulial space and the Ruliad and all that stuff has been sort of, it was imagined by Stephen at some point, and I think he was the one proposing the term Ruliad and so on. Is that right, Richard? Do you know about this? Nick,
I don't know the origins of the term, but
you remember, Nick, whether Stephen sort of coined the term at some point?
The Ruliad term?
Yes.
Oh, I remember almost exactly when we come up with it. I think it's like during some of our conversations with James Boyd and Stephen.
Right, with James Boyd. Yes. Right. So anyway, so I think there is a just to contextualize. There's a lot of interesting. There are many interesting questions surrounding this notion of the set of all possible programs, and because even how you parameterize such a space is contentious.
Mm-hmm.
What are the what programming languages do you write your programs on, and so on. Obviously you're going to use you can rely on some very general computer science theory and formal language theory to make some statements, but I think we probably want to be a bit more flexible than that, in the sense that to us it matters the sort of system that you end up working with finitely, even though at an infinite rate everything is computable in some equivalent sense. So I think it's very interesting that we still wonder about what is a good way to understand this. And so, for example, something I was working on very early on when I joined the Institute, almost as a warm-up exercise to get into Mathematica and so on, was to think about emulations between programs, and essentially looking at multi-way systems in one formal system and then multi-way systems in another formal system, and trying to see if they are somehow similar or something like that. So just to contextualize that, there is a lot of open questions in this direction of what the Ruliad is and how you should parameterize it, and even thinking of moduli spaces of programs that could be sort of some kind of cuts of the Ruliad and so on, and geometrizing all this might be part of the problem, and what kind of topology you put into it, and whether topology is even the right framework to analyze the space of programs, if there's such a thing as space. Anyway, just to contextualize that, there's a lot of interesting open questions there.
Yeah, no, that's very cool.
Yeah. Oh, sorry. This is also a question here on the chat. Is the Ruliad just Jonathan's comp category, COMP category?
Can't remember what that meant exactly.
He mentioned it on the recent interview. I was watching the one with Carl, the Theory of Everything podcast. Yeah.
Oh, Theory of Everything. Okay.
Yeah, it seems to me that they're equivalent, but there might be some sort of subtle differences.
I don't know the definition of that, but it might be effectively the categorical instantiation of that, right? Like it's categorical. Yeah. It's going to give you an instance of the Ruliad, or the space of all possible programs, blah blah blah. Set theory will give you one. Formal languages will give you one. Like it will have all these instantiations, and that's why I meant that we should be flexible in how we instantiate it. For example, I would probably say something like, "Oh yeah, if you give me labeled hypergraphs, you give me a universe of labeled hypergraphs and no possible rewrite rules between them, I can emulate all formal systems that we care about." So that's another instantiation. But there's a subtle question about how you instantiate that thing to talk about it, right? Let alone compute with it in practice. So yeah, it might be. I don't know the definition, so I can't really answer the question in chat. I don't know the precise definition of the comp category, but I imagine it's going to be the natural categorical instantiation of this kind of notion.
Yeah, I believe it was like the space of all sort of trivial data structures, and then all possible computations acting on them, or something like that. But it's and the discussion was really around it, like category 3 being kind of non-computational, but still able to capture these sets. So yeah. But yeah, speaking to what the point you were making, something like, say, Kolmogorov complexity theory is usually stated abstracted from the underlying computational system, but kind of means nothing unless you pin down, unless you decide, are we using Turing machines or some other computational substrate? So like the notion exists, but eventually you do need to kind of resolve that unknown. And in order to get sort of concrete results. And it's always with respect to the underlying computational system. If you change, then your complexity measures will change and so on. Yeah, so like a quick run through like some other things. I mean, some of these are kind of outliers. Like, for example, in the intervening time, Stephen, Nick and I were discussing like infinite computations even. How we would kind of encode these ordinals in Mathematica, and he sort of tasked me with looking at like Hydra, which kind of goes back to my winter school project, I believe, a little bit. So yeah, there was some sort of work into that, and I made some nice figures somewhere. And actually, I kind of noticed that there's this weird, at least visual similarity between if you use these material numberings and the Collatz graph, and that there could be nothing there, but they kind of at least look sort of similar in their behavior. So I don't know. Maybe there's something there to explore further. And there was some cool graphics, and I had them loaded up, but probably lost them. Let me know. So because these are not ordered in any sort of strict sense. And there's a whole bunch from the work of Stephen. So 1 second. Yeah, I think we should switch to that now. So,
yep.
And actually, it is still very relevant. So there's a kind of common thread throughout all of this, which is kind of interesting. Sort of like thinking of neural nets as programs, but they're programs which exist in a space because they're just some sort of vector of parameters which end up in your matrices and your weights and biases and so on. So again, Nick, Stephen, and I were conducting some experiments, and this is for the Alien Minds blog, which you can check out separately. And so I proposed this idea of like, well, why don't we take a network and then just damage it to various degrees and sort of see what happens. So we ended up with these kind of very strange initial experiments, which were quite funny. So this was like we're adding noise to the weights with some increasing scale, and everything became quite like a nice combination between experimental and theoretical, and a bit of sort of practical engineering. So here we have some image with no perturbation to the network, and then we're kind of gradually, I don't know, giving it Alzheimer's or something, whatever the equivalent would be biologically, I don't know, but we're just injecting noise into this network, and it's actually quite interesting how stable it is and how it's able to still produce this wolf, although it kind of gets this weird leg, and then eventually it sort of loses color, it has weird eyes at some point, and then eventually it seems to only focus on the face, and then suddenly there's a kind of transition to this silhouette, but it's still a wolf. There's kind of no way of understanding why this happens or anything, but now we have a grasp of something which you can kind of think of as a sort of program space, because now you have this essentially sort of vector representation of a program that's it's slightly different to say a program on a Turing machine or like a lambda calculus expression, in that it has a sort of fixed number of steps and it's bounded, but it's still sort of falls under the definition of a program. So here were some of our sort of initial experiments that we were doing, and I think I have another set where you can see like these artificial brain damage experiments, which and Stephen sort of came up with this notion of interconcept space. These networks are trained on billions of images, but somewhere in their representation space are things that are not of this world, or humans haven't yet named, or concepts which because we don't encounter them in the physical world, we don't have some sort of taxonomy for them, but they kind of arise in the sort of embedding space of these networks. So sorry, I've scrolled too far, and now this notebook is going to sit there for like 10 seconds, like buffering in. Actually, I think to be safe, we'll not look at
this space is kind of weird notion, because you assume that it's trained for the actual human data, right? So when is it going to come up with something that is not in the data? It's just of interpolation. 3. So I wouldn't call it interconcept, like something that actually has to be named while presenting something new.
Yeah, I tend to agree. I think, yeah, as we've discussed in that kind of gradient space discussion of networks and so on, like they're essentially kind of trying to reach a sort of zero in the sense of a zero as a PDE solution or something like that for every element of your training set. And so between, for example, between 2 points that you fit on a polynomial, it's just going where it wants to go, kind of thing. So yeah, it's kind of artificial. But I still think there's some sort of useful discussion to be had around like what's going on in that space. How has the network sort of constructed this embedding space so that it's meaningful? And when you stray away from the normal points that you get when you input something sensible, what is that stuff? And how is it composed of the training data? How has the training data influenced it, maybe? So yeah, maybe it's just mush, I don't know. But, you know.
Yeah, maybe just at least it learned some biases. So maybe interpolation is maybe a little bit meaningful.
Mm-hmm.
We can speculate.
Yeah. Let's see. Right, and then sort of subsequent to that blog project was the whole TED Talk thing. So actually that there are several notebooks for that, for how that was generated, and they're quite involved. And I think it sort of makes less sense to go through them and sort of more sense to show some of the partial results, to show the kind of journey for how we got to, you know, from idea to the final result. So let me just pull those out. I need to sort of navigate a little bit.
Yeah.
So I need to jump here, and then I think it's here. And here. Yeah. Yeah, in fact, we can actually just show like the kind of scale of what was going on. Lots of notebooks, lots of trying things out, and yeah. Let's see if I can pull out any of the partial results. So we kind of started out with these simple animations. In fact, some of the initial code was based off of something Max Piskunov had done, which kind of gave me a good starting point for how to sort of process the data. You can see that one kind of failed quite catastrophically, but then, you know, over time, sorry, I'm just clearing up the background. Over time, we were getting something a bit more stable, a bit more sensible. So I'm just going through each version. Oh, this one had an error, so every frame is red, and unfortunately, maybe that happened again. Maybe I fixed it. But yeah, initially it's like, okay, how do we get rid of this wobble? It's kind of annoying. How do we? So yeah, let's just try and skip ahead a little bit here. Yeah, and then we kind of arrived at sort of like a result somewhat like this, where we're growing a multi-way system and sort of controlling the camera, pulling it back as it's growing. You can see that there's still some issues of like wobble and so on that were quite annoying and quite difficult to remove.
So Richard, just I'm curious about the wobble. So you say that what was annoying and non-desirable about the wobble? Just
I guess it's subjective, but yeah, as it grows, you're kind of, depending on your evaluation order, it works better with random. But because what I'm doing is I'm sort of sandwiching simulation of the spring system, or this, it's kind of like an n-body plus spring system, right? And you choose some number of time steps to sandwich in between the model update steps, but as you're kind of increasing your and speeding up time, we're getting kind of more vertices being sort of dumped into the model.
Yeah.
But we keep the simulation steps fixed, so it kind of needs more time to sort of settle into its energy minimum.
But my question is what? So is this particular animation, the one that is now on the screen, was this too wobbly for? Or
I think so. I think it like
I love it.
Yeah, like,
it feels very organic. It feels great. I don't know. I mean,
actually, the comments on the YouTube were like, I think one of them was like, "It's the beating heart." Actually, on Steven's Twitter or something like that, it's like, "It's the beating heart of the universe."
Yeah.
It's like some poetic.
It's very poetic
thing.
I think just it feels like, you know what it feels like, because it looks like a web, like a spider web in there. It looks like if you looked at these spider colonies that build their webs in a time lapse, right? It has this feel, like organic feel of like things growing. I like it very much. Like these graphics, exactly. I love it. But anyway, that's just my aesthetics.
Yeah. So some of the issues encountered in this is that it's difficult to respond to sort of creative feedback when this maybe took an hour to generate, and you're sort of, you're like, okay, which parameter do I need to tweak? How much should I tweak it by? And like, was that successful? And it was quite a challenging sort of process, and I ended up having to write a bunch of like native code to take some of the output of some of our functions to more quickly generate the data I needed, so I could get kind of faster turnaround on these animations and so on. So there were four. There was like the universe, we had the black hole, so this was like from Jonathan we had some data of his numerical sort of relativity simulations coming from gravitas. And this one ended up being a lot more jumpy than I kind of hoped it would be, but just due to how the simulation sort of works, you get there's kind of a lot of noise with this stable structure. Sorry, VLC has this annoying playlist thing, which so you just close it and then load it back up.
So what is exactly being rendered here? What was the data from Jonathan, and what is being rendered?
So he's given me like a sequence of graphs that come from this gravitas framework, which he describes some sort of space-time. He sprinkles it and lets it run with Wolfram model updates, and he can speak to the finer details of like how that works and what's
but you're getting the sequence of graphs, right? Effectively.
Yeah, actually, and then we changed a little bit where I was getting an initial graph plus a sequence of edits, like a sequence of updates, essentially a sequence of events. But between each graph, a lot has changed, and so the only thing that's really stable are the black holes themselves. Again, it comes back to this question of like spatialization. It doesn't make sense to say that a point exists at a certain location in space, and when its neighborhood structure has changed, where do you put it? And so I was running the simulations until they relaxed to their sort of minimum energy between each update of his simulation. You've only got so many frames to work with, and so if we were allowing the simulation to relax between every one of his updates, it would look very slow and not so dynamic. So the unfortunate thing is that with today's like compression algorithms, this just looks like a mess, but it actually does look quite cool here watching it on the screen. I don't know if it comes across over Discord and YouTube, but
it looks good to me. I mean, I don't know. It looks cool.
Yeah. So this was nice to see, nice to work on, kind of collaborative effort.
Maybe you can expand the windows and make it more full screen so we see a bit more detail. But
I tried that.
Yes, that's great.
Yeah, and this one's actually running a bit more slowly, so you could kind of see. And as time goes on, you see the black holes kind of merge, and that's what you expect to happen. So that was cool. Actually, I have some other videos. I don't know how these are going to look. Oh no, this is some of my own thing that's not relevant. Let's see. We have some more. Okay. Yeah, we have some more exploding universe rough cuts where we're going for some highlight that shows you the recent event. That's let me see if I can get a better one. So it's trying to show you like what changed since the last rewrite.
Yeah.
And
that's very nice. That's a very nice visualization of hypergraphic writing.
And then on the multi-way thing. So again, this is a complete rough cut. This is like, okay, I've got some data out of the thing. I've managed to get like camera control sort of working within Mathematica. We can draw some edges between, these states in this multi-way states graph. And so there's 8 videos here. So there's, quite a lot of refinement going on. We've got various camera, pausing. Let's see. Okay, people quite liked when it was tilted on its side, although this angle is a bit too skewed. Something a bit weird going on here. Let me just zip through these until I get something else to say. Yeah, okay, so I think we settled on something kind of like this towards the end. In fact, in the end we ended up with something a bit like this, where we were branching out and showing states on each level. In fact, even showing branchial edges between the things. So, yeah, I mean, it was very challenging, because rendering time within the Wolfram language, at least for graphics of these size, was pretty prohibitive. So I know that I can do a lot more than this, but with the time that we had and with the constraints that we had, I think the results were cool. And
it's very time constrained thing for sure.
There's a question here: are these all 2D hypergraph plots?
No, those were actually 3-dimensional. I think they just ended up sort of laying out pretty flat. But on the next step here, there are actually some that sort of embed in 3 dimensions. It's just difficult to see, but yeah.
Because they are graphs, it's hard to get perspective.
Yeah, with a little bit of the camera motion, which is different in the final version, you sort of do see...
Like, the thing is, it's possible to tell that it's not a projected graph, because they are just pairwise graphs, right? But they are 3D.
Yeah, exactly. They're just two hypergraph. Yeah. So there's no way of telling. And Rolial Space was another one that we did, which we left right to the end. I thought it would be the easiest or whatever, because it's I don't know. With OBS running, the videos are doing something a little annoying. They're sort of pausing when it's decoding, but yeah. Right. Okay, and this ended up in some cool thing. If I can go back to it, maybe if I just pause it and jump to like a frame. So it's just trying to show Rolial Space as it grows. This one was based on Turing machines, but So those 4 videos. So that was project number 2 with Stephen. Project number 3 was the AI stuff. Can AI solve science? And for that we had a whole bunch of experiments. Like one of them was sort of building these autoencoders which try to essentially sort of spatialize cellular automata states. And can we use that to sort of predict some bulk set of future states as a way of probing the sort of computational irreducibility of the underlying system? So we found that with some rules, it's able to predict a little bit, but not every sort of future trajectory. So I guess that's a concrete example of sort of partial reducibility with some residual irreducibility of the system or something like that. So and we had a large number of experiments there. We looked at like using neural nets to predict trajectories in the 3 body problem. So here are some results. Again, you see like sometimes it does fairly well, other times it's completely hopeless and gets a little bit off, which really answers the question, can AI solve science, to a sort of definite no. Let's see. And there were some other questions about this one was some experiment I did on sort of function spaces. So can you use a neural net to, can you give it some samples from a function, get it to guess the function, and then kind of query the function at some other points that live outside of the samples that you provided it. And so in some cases it's kind of performing okay, and others not so okay. Let's see. We did a little work on genetic algorithms actually as part of that blog. We were trying to evolve CA rules So not using calculus in the way that we do in deep learning, where you have a gradient and you can kind of follow that with a small step size and so on, but instead making discrete changes to discrete programs. Surprisingly, we found that with some objectives we're able to. So this one was, we wanted to live for some prescribed number of steps, and if it goes too far, that's, it's punished for that. If it doesn't grow enough, it's sort of punished as well. But if it hits the nail on the head and grows to, say, exactly 50 steps, we say that's a winner. So this one was evolving 3-color, 3-neighbor cellular automata rules of this form, and finding rules which sort of satisfied some fitness function, which can be substituted for some other fitness function that you like. So, and we're actually still sort of exploring that at the moment. In the background, where I've actually managed to sort of train. Let me see if I can get the results for that somewhere here. Where is that going to be? See, autoencoder, function prediction. Oh wait, I'm in the wrong place. I have so many folders open to do this that I'm getting a little lost. 1 second. Yeah.
Yeah, just while you're searching for that, and that's what does it mean that the branchial graph is a unification description of the multi-way system? Just something that Jonathan had said. Is that going to be relevant for finding a minimal model of evolution? So it's just like a side comment. Maybe that's something Jonathan can answer better, I guess.
Yeah, is that from Eli? It might be. It sounds like a question from Eli.
Exactly.
Yeah. Yeah, we've been exploring these questions a little bit. So actually, the recent one was looking at these rule arrays, so where every cell can have a different cellular automata rule, and I've been able to separately, separate from these notebooks, using the GPU to actually do it, train them to recognize MNIST digits, which is sort of your benchmarks of problem that, or my first machine learning thing. So can we classify these handwritten digits? And I've managed to get it to about 25% error, which is surprising that it's even capable of doing that. So you sort of flatten these, and then you feed it to these rule arrays, which are, as I said, a different CA rule for each cell. And then you come up with some scheme to read out the final row. And, well, lo and behold, it turns out that you can do about, 3 out of 4 you can get correct. For the binarized MNIST, so not these with their real numbers. So that's a kind of sneak preview of something that we're doing in the background at the moment. Yeah,
that's very interesting. So what are you actually training here? What aspect is being trained?
So normally you would input this into some, say, convnet, like a convolutional neural network. And then you have some output neurons and like a loss function, and you just, do stochastic gradient descent. And nowadays people on MNIST can get like 99 point whatever, even on the validation set. But that's the same. Basically, we're applying the same problem, but to these rule arrays, which you can think of as a kind of like logic network in a way. Each of the CA rules is like a different sort of logic function, and it's a kind of network of, like you take your 3 inputs, output some new state, and each row is performing a step of the whole system. So your task is to basically select, between these pink and yellow things, is there some configuration which minimizes the error for this task here? So that's literally what it is. I'm trying to find the workbooks. Actually, I know why I couldn't find them, because I put them on Dropbox. But yeah, searching for these things during a live stream where you're like, oh no, it's a bit. Yeah, I found. I don't know if you experience this, but your brain can sometimes blank when you're in
Yeah.
public setting. But anyway, here are the loss curves for those. So it's like, it's actually learning something. This is similar to what you get when you're training a deep network, where you have a loss that's sort of asymptotically approaching the answer. And here's one of the rule sets. This one actually uses 4 different CA rules that were pre-selected. This is seeing how it changes. So as I'm scrolling this, you're looking at different generations, essentially, towards the end. This plot here is showing you the mutations that were present so anytime this graph makes a jump down, then I generate an image for the sequence. So, and I don't know if you can actually see it due to compression and so on, but this is showing you that, yeah, in the beginning the mutations are quite sparse, but as you get towards the end, it seems to go further distance to find something better, which...
Can we zoom in on this a bit, Richard? Like, just run the animation again.
See, the problem is when you zoom a frame on these things, then you only get the first frame. Wait, hold on. I could maybe just, like, do this. I don't know if that makes it any better. All right.
Yep.
So yeah, so those are the mutations which were responsible for an improvement. So you're not seeing kind of all the mutations, you're seeing only those which resulted in a better solution to the problem as time goes on.
And the one just before that, that one was also interesting, if you could replay that.
Oh, yeah, no worries. Yeah. So you can't see much. It's basically the same as what you see below, but you're looking at the actual rule, not just the delta. So you see like this sparse kind of sprinkling of changes, and then what happens here is that because sometimes you can wait a while to do better, a lot of mutations are kind of building up, and then you only see so they kind of get flattened, and that's why you see some of the frames have more mutations kind of accumulated by the time I generate a frame of this thing. So yeah. No, wait, let me just reset this thing because so that's my whole screen and now I have to do this, so just bear with me.
Can you zoom in on the notebook itself? What's the command? I think Control Plus.
Oh, right. Probably there's a smarter way of doing it. I think there's like, there is magnification, but yeah. I don't know how well that would do. Yeah, this is a little annoying because it's...
That's very fascinating, the fact that you can train these things. I think that concept is just pretty incredible.
Yeah, and it was kind of unexpected, actually, that we would even be able to do it. So it's sort of a surprising result, and it's just... Yeah, so this is for the sort of next blog where we're looking for like a minimal model of biological evolution. Again, another kind of rulal journey. So I actually have another few from these where... so here's some more loss plots. This is where you allow all possible rules, actually. And again, actually, if I just, as you said, if I just apply some magnification, there we go. Is that better? That's better.
Yep.
Yeah. So again, you get this kind of sparse updates and then more towards the end, some mutations. But the difference here is that, look, it thinks a 3 is a 3, it thinks a 9 is a 9, and or... Okay, sometimes it makes mistakes. That 1 looked like a 5, but this one looked like a 1. That 2 is a 2. That 7 it thinks is a 9. You can kind of excuse it. So that 0 is a 0, that 8's an 8, that 4 is a 4. Thinks that 7 is a 9. Sorry, I had to clear my throat. And this is the confusion matrix, which, I mean, in the ideal case, you want to see like a diagonal with 100% down the diagonal, and the off diagonals are telling you, like, it was a 1, but you thought it was a 9. This one is actual by predicted, although I may have had it wrong. That's, actual by predicted, So, and that's it in sort of number form. Then I noticed, actually, with these networks, if you do ensemble averaging, so if you instead of binarizing the inputs, if you take a sample from them. So based on the brightness of the pixel, you sample a random number. So if it's white, it will always be on. If it's black, it will always be off. If it's gray, it will be 50-50, let's say. If you do, say, like 5 averages of the evolution of that system, you can actually get the error. In this case, it went from 40 down to like 25% error. So that's why I say it gets 3 out of 4 correct. And that's interesting because that wasn't being applied during training. So during training, it only gets 1 guess. It doesn't get to sample from that training sample multiple times. But if at inference time you do that, you end up with improved results. So from 42 to 25% error with 16 samples, not 5. Sorry, it's 16 samples gets you that. But it's weird. It doesn't seem to sort of monotonically decrease. It sort of went up a little bit, but that could be just through luck. I don't know. And here are the samples with the ensemble averaging. So 7 is a 7, 4 is a 4, 9 is a 9, 7 is a 7. Okay, 1 is a 0, 0 is a 0. We'll just ignore when it gets it wrong. But yeah.
So
all right, let's go back to.
Yeah. Just to note on time, like I think we're doing okay, but maybe we can sort of move to the final bits of this live stream, and maybe if there's
I agree.
questions.
I think that would be good.
Yeah. So
that's like a kind of quick run through of sort of all the projects that we've been working on. Yeah.
Yeah, that looked very intense and diverse, very I guess institute-like in that sense.
Mm-hmm.
Anyway, questions. Do we have something from chat or Nick, Xerxes? Would you like to ask something more specific?
I can start off with one here. So a little bit earlier, there was a comment. Category theory has the restriction on of compositionality of morphisms. So the Ruliad might be more general.
What is the comment again? Can you say it again?
Yeah, so category theory has the restriction of compositionality of morphisms. So that's a restriction in category theory. And perhaps the Ruliad is more general than that.
Yeah. I think that commenting on the category theory side of things, you have these different ways of presenting formal systems and mathematics that are universal, right? Like you can recover the moment you know that you can recover things like set theory, and with either category theory or Merrill-Frankel standard stuff, and type theory. These kinds of formalizations, they are at some level formally identical or equivalent, but I think it really matters how you instantiate your formal systems, because when you get into the actual computations, and this is exactly what Richard has been showing. I mean, he's very much an actual computations person here. I mean, you've shown all these programs running and actually having to deal with finite compute time and finite steps and so on. Then the instantiations become extremely relevant, and then how you are. It's not the same thing to just trying to do a symbolic parser to do type theory and to do some automated theory improving than to deal with direct graph topology and rewriting rules on graphs. I mean, these can be shown to be equivalent for the sake of modeling the whole of mathematics or recovering foundations of mathematics like set theory and so on. But in practice, the way that you're going to go about them is extremely different. So this comment about the compositionality of morphisms being somewhat a limitation of category theory. I mean, I wouldn't even call it a limitation. It is what category theory is, right? It's it's this idea of compositionality of morphisms. And so the only comment I have to make in that direction is that category theory is extremely directed. It has the source, target, input, output framework sort of baked in. And the whole formalism runs on that kind of paradigm. But you can imagine, as long as you have some notion of process or time or computation in general, you don't need the directionality. You can have data structures that are completely that are heterogeneous. They involve directionality and non-directionality and things like that. I mean, that's not the main point, but that's certainly one of the aspects. So yeah.
So yeah, I was watching a stream with Jonathan talking about this, and I think it was mentioned that in category theory you can recreate what's happening in undirected graphs, but you have to do some extra work to make it undirected. You kind of have to like do some forgetful function or something.
Yes.
Is that accurate?
Yeah. Yes. So one thing is that when you treat things categorically, it really matters whether you're dealing with directed graphs, undirected graphs, hypergraphs of a certain kind or another. And there's this theory of what's called combinatorial species that essentially tells you what the possibilities are in terms of what data structures you can build. So if you're thinking of using this data structures, this combinatorial species as your building blocks, so to speak, so to compose them and to sort of attach them to one another, you get very sensitive behavior in if you want to encode categorically, right? And it's interesting because the category theorists, I've been in close communication with many of the people that are doing the very technical work on sort of the category theory angle of hypergraph rewriting. And it's very difficult to try to do general category theory of hypergraph rewriting in a theoretically sound sense. And the reason is not very surprising if you think about it, because at the end of the day, when you can do general rewriting, it means that you have this infinite flexibility, right? You're not restricting yourself to, for example, to composition. I think the comment refers to is this idea that whenever you have the conformality of a morphism after morphism, then you just sort of transitively complete and you rewrite the output. It's much more diverse than that. The topologies that can compose and the things that can rewrite and the sort of partial matching that can happen and sort of all the causal branching that might result from that partial matching and so on. It's much more complicated. And so it is uglier for traditional mathematics, and it doesn't go well with traditional mathematics, because traditional mathematics has almost been, you can imagine that it has almost been selected to be this very refined and finitary language, and therefore it's very well adapted for situations that are not so ugly and conflicted. But that's kind of what's going on there. The rewriting framework allows for a much more flexible, yet theoretically less satisfying and theoretically less closed approach. But trade-offs.
There is, of course, something called what people refer to as higher dimensional rewriting, and there you can express things category theoretic, but not in the standard categories. What you can do is, so one of the so-called restrictions, or what might appear like a restriction, is that when you just take ordinary categories, you have associativity, and that is just hardwired there. Now, when you instead move to higher categories, you can relax these associativity axioms. You can have weaker notions of associativity, and then you have the benefit of higher morphisms. And these higher morphisms give you more structure than just a category. So in that sense, when typically one wants to discuss anything to do with radial space or Reuliad, etc., apart from these other issues that Carlos just mentioned about insensation, which actually are very important, you also have to keep in mind that categories may not actually be a complete description. In a lot of descriptions, in a lot of cases, you will very necessarily need to go to some higher category. And on the type theory side, that corresponds not just to ordinary type theory or per Martin-Loff intuitionistic type theory, but you might then necessarily be pushed or forced into what is called homotopy type theory. And that, of course, comes with some of its interesting topological connections, some of which Richard alluded to earlier. So in many interesting instantiations, whether you're working with string rewriting systems, hypergraph rewriting systems, etc., once you kind of specify the setup you're working with, you will and you want to study Reulian space for that instantiation, you'll end up necessarily going into the world of higher categories, and that offers you a much kind of broader thing. So in many ways, I would say that it depends again on the case that you're dealing with, but often when one is really talking about the Rullial space or even the Rulliad, which is a term that sometimes one wonders what mathematical object it is. In many cases, it's not going to be described by a standard category. It will be some of the possible classes of infinity categories. Now, it really depends. Certain instantiations are in fact what is called infinity one categories. Other instantiations may be other classes of infinity categories, but it will be one of those simply because this weaker notion of associativity and weaker notion of what is called the unit axiom allows you for more structure. And so that kind of gives you more flexibility into the geometry of types. In the rewriting side, people call this higher dimensional rewriting. In the type theory side, it's called homotopy type, and of course, on the program side, it corresponds to programs that programs are proofs in some sense, and these are proofs corresponding to higher morphisms. So there's a whole geometry and structure on that side of things. Now, there is one kind of important point which is very closely related to what Carlos said. Even if you go for higher categories, you are still just taking this sort of notion of arrows and building up higher arrows. But if you really want to get beyond that, you need to ask even what is outside of categories. Then you go to something that's higher arity right from the beginning. So higher categories is one way to build higher structures. Higher arity is another way to build higher structures. In the most generality, one needs a clever formalism that uses both these kind of ways of extension, and that is quite difficult to specify mathematically.
Very interesting.
Yeah. All right.
Very, very interesting.
Some more comments, questions. I think we've gone for a good length. I think that was a very, very good summary, Richard. That was great.
Yeah. If I could provide a kind of closing animation,
absolutely,
that would be cool.
Maybe
food for thought.
Yes.
There's the risk that it'll also stimulate further discussion. But anyway, so I've been kind of on break for the last week whilst we sort of switch over at the Institute, and so I coded up this thing here, which people can see. It may be related, it may not be related, but essentially what you're looking at is this iterated function system. So, and we see iteration everywhere. You know, in the Wolfram Physics project, when you apply a rule to a particular hypergraph, you're essentially just applying a function to some object and so on. And this has, in some sense, got multi-way sort of embedded in it, because every point is sort of under the action of each of these. So there's a sort of set of attractors, not just one, and they're sort of chosen stochastically. So, you know, you start with some point on the unit interval, you pick a random function, and you update your point according to that thing. So there's a kind of weird notion of like, who's eating who? You know, is this point being acted upon by like function 1 or function 2, and in what sequence? Is it function 1 then function 2, or function 2 and then function 1? We just don't know. It's kind of some weird mixture between the two. But if you carry on this process and you color individually each function with a different unique color, you get images like this. And these are parameterized by just some vector of values which you use as, say, some coefficient to some polynomial, or some multiplier for some term inside some trigonometric function, whatever. You can set it up however you like. But in some sense, watching this video, you're watching a small piece of this sort of multi-way function space, and we're sort of moving around some neighborhood. So I thought to kind of close things off, this would be a kind of interesting thing, that just thinking about things taken to their infinite limit, although this is some kind of finite sampling of such a system, that when you have these contraction operations applied to some set, you yield these interesting objects. And I don't know, I like making pretty pictures with programs, so here's one that I just did. And this again is also GPU accelerated, so you can generate these in real time and have fun exploring the space of all functions or whatever.
Wow, that's amazing. That looks great.
So there you go, multi-way and Rullial sort of, if you really Squint your eyes, maybe.
Indeed. Well, that was fantastic, and it's a beautiful way to close it. Just to thank Richard again and all the Institute members here. Remind everyone that they can follow the link. Maybe James, you can post the link to the community on the YouTube chat. Look forward to meeting you on our Discord server. We are open to conversations and to engage with you openly. That's part of the mission of the Institute. And I don't know if you, James, wanted to have some closing comments as well, but I think this is a very good place to stop.
Yeah, can you hear me?
Yep.
I think very importantly, this is open science, right? So all of these notebooks will be available for everyone to play with.
Mm-hmm.
So I think pick up from where Richard left off here and let your imagination flourish in the computational universe.
Indeed. Exactly.
Great.
Right, everyone. Good to see you, and I'll see you soon in one of our live streams. Goodbye.
Bye, everyone.